Alright, so we have an equation. This is an important kinematic equation. So basically it says v final squared is equal to v initial squared plus 2a delta x. Or 2 times acceleration times displacement. So this is cool. I'm gonna do something cooler. I'm gonna derive the equation. So to derive the equation, I'm not gonna do something crazy using derivatives and integrals and definition of acceleration and stuff like that. I'm gonna use energy. Right? I'm gonna use the work energy theorem. So I'm gonna write that real quick. So work energy theorem is basically, well, net work is equal to change in kinetic energy. Alright? So that's great. So let's think about this. What is net work? Right? Well, what's the formula for work? That's force times displacement. So net work, I just net force times displacement. So I'll write like this here. Net force times displacement delta x. And that's equal to change in kinetic energy. Alright, change in kinetic energy. But wait, what's the change in kinetic energy? Well, that's just final kinetic energy minus initial kinetic energy. But what's the kinetic energy formula? That's 1/2 mv squared. So kinetic energy final kinetic energy, whatever you want to call it, I just 1/2 mv final squared minus kinetic energy initial. Well, that's just 1/2 mv initial squared. Alright, that's great. But let's take a look at F net delta x, right? So what's the formula for force? Well, Newton's second law, force equal to mass times acceleration. So net force, that's just mass times net acceleration, and then just times delta x. Get rid of the middleman, change the kinetic energy. I just write 1/2 mv final squared minus 1/2 mv initial squared. Alright, that's great. So, alright, so here's the thing. We have net acceleration here where kinematic has acceleration. Really, they all mean the same thing because in the kinematics equation, acceleration is just one vector, just the total acceleration. Net acceleration, that's also one vector. That represents total acceleration. So for kinematics purpose, we'll just call this A. Alright, so I'll just, well, alright, so first things first. Look at this 1/2 mv final squared minus 1/2 mv initial squared. I take a look at this. I can pull a big brain move real quick because I can factor out the 1/2 m, right? So just rewrite this as 1/2 m, alright? So we're left with v final squared minus v initial squared. So let's see, v final squared minus v initial squared. Alright, that's great. And that's equal to mass times acceleration times delta x. Now look at this. Alright, you see mass here, they get cancelled out. So we're left, alright, this is getting kind of messy. I'm gonna write it right here, just rewrite this. So let's see here, mass cancel out, so we end up with acceleration times delta x, alright, is equal to 1/2 times v final squared minus v initial squared. Alright, so, we're basically at the home stretch. I think I'll multiply both sides by 2, because I hate fractions. So let's see, I'm gonna write it right here, alright? So, v final squared minus v initial squared, that's equal to, well, multiplied by 2, right? So 2a delta x. Now I want to find v final squared, so I'm going to just add v initial squared to both sides, and we'll get v final squared is equal to v initial squared plus 2a delta x. Or basically the same thing we wrote right here. So, yeah, it's pretty cool, right? So, nice derivation, pretty important kinematic equation. Follow for more things like this, and yeah.